For 25 years, scientists believed they had solved the universe. One elegant model explained nearly everything: the age of the cosmos, its shape, its composition, how galaxies formed and where they were heading. It was the most successful framework in the history of physics. Then the James Webb Space Telescope opened its golden eye, and almost immediately, cracks began to appear. Not in one place, in several. The universe is expanding at a rate that contradicts itself. Galaxies that should not exist are sitting in the ancient dark. The cosmic scaffolding is less clumped than it ought to be. And the force driving everything apart may not be constant after all. Something about our deepest model of reality may be incomplete. And Webb may be the very instrument that is forcing us to face it. If this is the kind of science that pulls you in, consider hitting like and subscribing. We go deep on the questions that actually matter. Are you comfortable? Now, let's begin. There is a model that describes almost everything. Not a physical model sitting on a desk somewhere. Not a computer simulation running in a single laboratory. A mathematical framework so precise, so thoroughly tested, and so consistently confirmed by observation that for more than 2 decades, the overwhelming majority of working cosmologists treated it as settled. It explained the age of the universe. It explained the shape of space. It described what the cosmos is made of, how structures formed within it, and where everything is heading. It matched observations spanning 13.8 billion years of cosmic history with an accuracy that bordered on absurd. It is called the Lambda Cold Dark Matter model, Lambda CDM for short. And before the James Webb Space Telescope opened its instruments to the sky, almost no one expected anything to seriously challenge it. To understand why that confidence existed, and why the pressure now building against it matters so deeply, you need to understand what this model actually claims and how it earned the trust of an entire scientific generation. Start with the most basic question cosmology tries to answer. What is the universe made of, and how did it get to be the way it is? For most of human history, the answer to that question was mythology, gods and creation stories. It was not until the 20th century that physics began to provide a testable framework, and it was not until the final years of that century that the framework became precise enough to call a standard model. Lambda CDM rests on a set of claims that sound deceptively simple when stated plainly. The universe began in an extraordinarily hot, dense state, roughly 13.8 billion years ago. It has been expanding ever since. That expansion is governed by general relativity, Albert Einstein's theory of gravity, which describes how matter and energy curve the fabric of space-time. The contents of the universe determine how that expansion behaves. And according to the best measurements available, those contents break down into 3 components. Ordinary matter, the atoms that make up stars, planets, gas clouds, and every person who has ever lived, accounts for roughly 5% of the total energy budget of the universe. That number alone should stop you. Everything you have ever seen, every galaxy photograph, every nebula, every supernova remnant, every planet in every solar system across the observable cosmos, all of it is 5%. A thin film of substance stretched across an ocean of something else. The next 27% is dark matter. It does not emit light. It does not absorb light. It does not interact with ordinary matter through any force except gravity. We have never directly detected a dark matter particle. But its gravitational influence is written across the sky, in the rotation curves of galaxies, in the way galaxy clusters bend light from objects behind them, and in the pattern of how cosmic structure formed over billions of years. Without it, the mathematics of galaxy formation collapses. Stars would not hold together in the configurations we observe. The cosmic web, the vast filamentary network of matter stretching between galaxy clusters, would not exist in its observed form. Dark matter is invisible, but its fingerprints are everywhere. The remaining 68% is something even stranger: dark energy, a property of space itself that drives the accelerating expansion of the universe. Its discovery in 1998 by two independent teams studying distant Type Ia supernovae was so unexpected that it won the Nobel Prize in Physics in 2011. The universe was not just expanding, it was expanding faster and faster. Something was pushing it apart, and that something appeared to behave exactly like a cosmological constant, a fixed energy density woven into the fabric of space-time that does not dilute as space stretches. Einstein had introduced a cosmological constant into his equations almost a century earlier, and then abandoned it. The universe brought it back. Those three ingredients, ordinary matter, and dark energy, plus the laws of general relativity, form the foundation of Lambda CDM. Lambda refers to the cosmological constant. CDM refers to cold dark matter, meaning dark matter particles that move slowly compared to the speed of light. Together, they produce a model that makes precise, testable predictions about the history and structure of the cosmos. And for over 2 decades, nearly every major observation confirmed those predictions to an extraordinary degree. The single most important piece of evidence came from the sky itself, or more precisely, from a faint glow that fills every direction of space: the cosmic microwave background. It is the oldest light in the universe, released roughly 380,000 years after the Big Bang, when the cosmos cooled enough for atoms to form and photons to travel freely for the first time. Before that moment, the universe was a dense, opaque plasma. After it, light could move. And that first light has been traveling ever since, stretched by the expansion of space from visible wavelengths into microwaves, filling the cosmos with a nearly uniform glow at a temperature of roughly 2.7 degrees above absolute zero. Nearly uniform, not perfectly. And that imperfection is where the power of the model resides. Embedded in the cosmic microwave background are tiny temperature fluctuations, variations of roughly 1 part in 100,000 from one patch of sky to another. Those fluctuations are the seeds of everything. They represent the slight density differences in the early universe that gravity would amplify over billions of years into galaxies, clusters, filaments, and voids. The pattern of those fluctuations, their sizes, their relative amplitudes, the way they correlate across different angular scales, encodes an extraordinary amount of information about the contents and geometry of the universe. 3 successive space missions mapped this pattern with increasing precision. NASA's Cosmic Background Explorer, known as COBE, detected the fluctuations for the first time in 1992. NASA's Wilkinson Microwave Anisotropy Probe, known as WMAP, mapped them in exquisite detail, starting in 2001. And the European Space Agency's Planck satellite, launched in 2009, produced the most precise full-sky map of the cosmic microwave background ever made. The data from Planck, released in its final form in 2018 and refined in subsequent analyses, remains one of the most important datasets in the history of science. What Planck showed was remarkable. The pattern of fluctuations in the cosmic microwave background matched the predictions of Lambda CDM with an accuracy that stunned even the scientists who built the model. The positions of the peaks in the angular power spectrum, the ratios of their heights, the damping of fluctuations at small scales, all of it lined up with what the model predicted given a specific set of parameters. The age of the universe. The density of ordinary matter, the density of dark matter, the geometry of space, the amplitude of initial fluctuations. Planck measured all of them simultaneously, and they all pointed to the same coherent picture. Space is flat, meaning the geometry of the universe on the largest scales is Euclidean, not curved like a sphere or a saddle. The universe is 13.8 billion years old, give or take a few tens of millions of years. The density of ordinary matter is precisely what nucleosynthesis models predicted from the abundances of light elements forged in the first few minutes after the Big Bang. Everything fit. But the cosmic microwave background was not the only pillar holding up the model. The second was the large-scale structure of the universe. Galaxies are not scattered randomly across space. They are organized into a vast cosmic web, a network of dense filaments, sheets, and clusters surrounding enormous voids where almost nothing exists. This structure is a direct consequence of the gravitational amplification of the fluctuations imprinted in the cosmic microwave background. The same initial conditions that produced the pattern Planck measured also produced, over billions of years of gravitational collapse, the galaxy distribution we observe today. Surveys mapping millions of galaxies, such as the Sloan Digital Sky Survey and the 2-degree Field Galaxy Redshift Survey, confirmed that the distribution of galaxies on the largest scales matches the predictions of Lambda CDM. The statistical properties of galaxy clustering, the correlation functions, the power spectrum, the distribution of cluster masses, all agreed with simulations based on the standard model, to a degree that left very little room for alternative frameworks. There was a third pillar as well, the expansion history itself. Measuring how fast the universe is expanding at different epochs tells you how the balance between matter and dark energy has shifted over cosmic time. In the early universe, matter dominated. Its gravitational pull slowed the expansion. As space expanded and matter diluted, dark energy, whose density remains constant as space stretches, gradually took over. The transition from deceleration to acceleration happened roughly 7 billion years ago. Since then, the expansion has been speeding up. This history is measured using standard candles and standard rulers. Type Ia supernovae are the most famous standard candle. These are thermonuclear explosions of white dwarf stars that, under certain conditions, produce a remarkably consistent peak brightness. By comparing how bright a Type Ia supernova appears to how bright it actually is, astronomers can determine its distance. Comparing that distance to the supernova's redshift, the stretching of its light caused by the expansion of space reveals how fast the universe was expanding when that light was emitted. Baryon, acoustic oscillations, are the standard ruler. In the early universe, sound waves traveling through the hot plasma left a characteristic imprint on the distribution of matter. A preferred separation scale between concentrations of galaxies that can be measured at different epochs. That scale acts as a cosmic yardstick. By tracking how it appears to change at different distances, astronomers map the expansion history directly. Both methods, when applied within the Lambda CDM framework, gave consistent results. The universe was expanding in the way the model predicted. Dark energy behaved like a cosmological constant. The deceleration to acceleration transition occurred at the right time. The numbers lined up. This is the picture that was in place when the James Webb Space Telescope was being designed, built, and launched. A model with 3 major pillars of observational support, each tested independently, each confirmed to high precision: the cosmic microwave background, the large-scale structure, the expansion history. Together, they told a story so consistent, so interlocking, that challenging Lambda CDM required not just finding an anomaly, but finding one that could not be absorbed by adjusting the details. What made this convergence so powerful was not just that each pillar supported the model. It was that all 3 pillars built from completely different observations, using completely different instruments and completely different physical processes, independently pointed to the same set of numbers. The age of the universe, derived from the cosmic microwave background, matched the age implied by the expansion history. The matter density measured by Planck matched the density required by galaxy clustering surveys. The geometry inferred from the microwave background matched the geometry confirmed by supernova data. These were not three ways of checking the same measurement. They were three fundamentally independent windows into the universe, and behind each window was the same picture. In science, when independent lines of evidence converge on a single answer, the result is not merely confirmation. It is the closest thing to certainty that the empirical method can provide, and there was something else that made the confidence run deep. Lambda CDM is not a vague idea. It is a quantitative model with only 6 free parameters, 6 numbers. When plugged into the equations of general relativity and the physics of the early universe, generate predictions for everything from the pattern of the cosmic microwave background to the distribution of galaxies billions of years later. That is an extraordinarily lean framework. Most physical theories require far more parameters to describe far less. The fact that 6 numbers could describe the observable universe with the precision that Planck confirmed was, in the eyes of most cosmologists, one of the greatest achievements in the history of science. It is worth pausing here to appreciate what that means. Imagine trying to describe every city, river, mountain, and ocean on Earth using 6 numbers. The idea sounds absurd. Yet that is roughly the level of ambition Lambda CDM operates at. 6 parameters. 13.8 billion years of cosmic evolution. A universe containing hundreds of billions of galaxies, each containing hundreds of billions of stars. And the model works, or at least it worked, to the precision of the instruments available before 2022. Now, here is where the James Webb Space Telescope enters the story. And it is critical to understand what Webb was designed to do, because it was not built to overthrow cosmology. It was not a rebel instrument sent to challenge the establishment. It was the establishment's own tool, designed to do what good science always does: measure things better, see further, fill in the gaps. Webb is the most powerful space telescope ever constructed. Its primary mirror spans 6.5 meters, more than 2.5 times the diameter of the Hubble Space Telescope's mirror. It observes primarily in infrared wavelengths, which means it can see through dust that blocks visible light and detect light from the most distant and ancient objects in the universe, light that has been stretched by cosmic expansion from ultraviolet and visible wavelengths into the infrared. It sits at the second Lagrange point, roughly 1.5 million kilometers from Earth, orbiting the Sun in gravitational lockstep with our planet, shielded from solar heat by a sunshield the size of a tennis court. It was conceived in the 1990s. It took more than 2 decades and roughly $10 billion to build. It launched on Christmas Day, 2021, and when it turned its instruments toward the deep universe for the first time, the expectation in the cosmological community was clear. Webb would refine the picture. It would sharpen the measurements. It would fill in the details of galaxy formation, star formation, and the chemistry of the early universe. It would confirm the timeline that Lambda CDM predicted. It would add resolution to a story already believed to be fundamentally complete. The Hubble Space Telescope had spent 3 decades building the observational foundation. Webb was supposed to extend it. The cosmic distance ladder, the chain of measurements linking nearby stars to distant supernovae to the expansion rate of the universe, had been constructed with Hubble's data. Webb would check that ladder. Its sharper infrared vision would separate Cepheid variable stars from their crowded surroundings in distant galaxies, removing potential sources of error. Its sensitivity would reach galaxies farther away, testing whether the measurements held up at greater distances. The early universe, visible only as faint smudges in Hubble's deepest images, would come into focus under Webb's gaze. Astronomers expected to see small, young galaxies in the first billion years after the Big Bang, fragile structures in the earliest stages of assembly, taking their first steps toward becoming the mature systems we see in the nearby universe. Those early galaxies would confirm the Standard Model's timeline of structure formation. Gravity pulling matter together gradually, small structures merging into larger ones, stars forming at modest rates dictated by the physics of gas, cooling, and feedback. That was the expectation. A tool built to confirm and refine. A next-generation instrument designed to turn the final pages of a story most cosmologists believed they already knew the ending to. The confidence was not arrogance. It was earned. Lambda CDM had passed every test thrown at it for more than 20 years. Multiple independent observational programs, using different instruments, different methods, and different parts of the electromagnetic spectrum, had converged on the same set of parameters. The model was not a guess. It was a framework that had survived extraordinary scrutiny. But there is a difference between a model that has survived every test and a model that has survived every possible test. There is a difference between a framework that works at a certain level of precision and one that works at every level of precision. And there is a difference between confirming a model with the instruments you have and testing it with an instrument sharper than anything that came before. That difference is what the James Webb Space Telescope was about to expose. Because when Webb began delivering data, what it showed was not a clean confirmation of the standard picture. It was something more uncomfortable. Something that did not break the model outright, but refused to sit quietly inside it. Measurements that were supposed to converge began to diverge. Objects that were supposed to fit the timeline appeared in the wrong places. And a disagreement that had been simmering for years in the expansion data, a disagreement that many hoped would be resolved by better instruments, was not resolved at all. It was confirmed, strengthened, sharpened to a statistical significance that made it very difficult to dismiss. The model that had explained almost everything was about to encounter something it could not easily explain. Not one thing, several. And the question that cosmologists would be forced to confront was not whether Lambda CDM was useful. It clearly was. The question was whether it was complete, whether the 6 parameters that had described the universe so successfully for 2 decades were missing something. Whether the most successful model in the history of physical science had been telling us almost the whole truth, but not quite all of it. What happened next started with a number that had been argued about for nearly a decade, a number that describes how fast the fabric of reality itself is stretching apart. And when Webb measured the stars used to calculate that number with the sharpest infrared eyes ever built, the answer did not settle the argument. It made the argument worse. The number that matters most in this story is called the Hubble constant. It is written as his zero, and despite its name, it has been anything but constant in the arguments it has caused. The Hubble constant tells you how fast the universe is expanding right now, not in the past, not in the future, right now. It is expressed in a unit that sounds technical, but is actually straightforward: kilometers per second per megaparsec. A megaparsec is roughly 3.26 million light-years. So, when a cosmologist says the Hubble constant is 73, they mean that for every megaparsec of distance between you and a distant galaxy, that galaxy is moving away from you at 73 kilometers per second. The farther away something is, the faster it recedes. The universe is not expanding into anything. Space itself is stretching, and the Hubble constant measures the rate. Getting this number right is one of the most important tasks in all of cosmology. It determines the age of the universe. It constrains the density of dark energy. It affects calculations about the ultimate fate of everything that exists. If you get H0 wrong, you get the universe wrong. And for nearly a decade before Webb launched, two different ways of measuring it were giving two different answers. Both methods were sophisticated. Both were conducted by world-class teams. Both had been checked, rechecked, and refined to extraordinary precision, and they refused to agree. The first method starts nearby and works outward. It is called the local measurement or the distance ladder approach. The idea is to build a chain of overlapping measurements, each calibrated against the last, reaching from stars in our own galaxy out to galaxies hundreds of millions of light-years away. The first rung of this ladder uses geometric parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars. The amount of shift tells you exactly how far away the star is. No assumptions required. Pure geometry. But parallax only works for relatively nearby stars, out to a few thousand light-years at most. The second rung uses a special class of stars called Cepheid variables. These are giant stars that pulsate in brightness with a regular rhythm. In 1912, astronomer Henrietta Swan Leavitt discovered that the period of a Cepheid's pulsation is directly related to its true luminosity. A Cepheid that pulses slowly is genuinely brighter than one that pulses quickly. If you measure the pulsation period, you know the star's true brightness. Compare that to how bright it appears from Earth, and you can calculate the distance. Cepheids can be seen in galaxies tens of millions of light-years away, extending the ladder far beyond what parallax alone can reach. The third rung uses type Ia supernovae. These violent stellar explosions, the brightest standardizable events in astronomy, produce a remarkably consistent peak brightness that allows them to serve as distance markers visible across billions of light-years. By calibrating the brightness of type Ia supernovae against the Cepheids in the same host galaxies, astronomers extend the ladder to cosmological distances deep enough to measure the expansion rate of the universe directly. This chain of measurement, from parallax to Cepheids to supernovae, has been refined over more than a century. And the team that has pushed it to its greatest precision is led by Adam Riess, the Nobel laureate based at Johns Hopkins University. Riess and his collaborators, working under a program called SH0ES, which stands for supernova SH0 for the equation of state, have spent years building the most precise local measurement of the Hubble constant ever achieved. Their result, consistently reported across multiple analyses and using data from the Hubble Space Telescope, is approximately 73 kilometers per second per megaparsec. The uncertainty on that number has been squeezed down to roughly 1 kilometer per second per megaparsec. It is an extraordinarily tight measurement. The second method does not start nearby. It starts at the beginning of time. By analyzing the pattern of temperature fluctuations in the cosmic microwave background, the ancient light released 380,000 years after the Big Bang. Cosmologists can extract the precise composition and geometry of the early universe. Those parameters, when fed into the equations of Lambda CDM, predict how the universe should have evolved over the following 13.8 billion years, including how fast it should be expanding today. The Planck satellite performed this measurement with the highest precision ever achieved. Its result for the Hubble constant derived not from observing the expansion directly, but from calculating what the expansion rate should be given the early universe's conditions and the standard model, is approximately 67.4 kilometers per second per megaparsec, 73 versus 67.4. The gap between these two numbers may not sound dramatic in isolation. But in the context of the precision with which both measurements are made, it is enormous. The uncertainties on each measurement are small enough that the two values are separated by more than 5 standard deviations. In statistics, 5 sigma is the threshold at which physicists declare a genuine discovery. The probability that this discrepancy is a random coincidence, given the reported uncertainties, is less than 1 in a million. This disagreement is the Hubble tension, and it has been haunting cosmology since the mid-2010 era, growing sharper with every new round of measurements. Now, here is what made the tension tolerable for a long time. There was always a plausible escape hatch. The distance ladder is complicated. Each rung introduces potential sources of error. Cepheid, variable stars in distant galaxies are not observed in isolation. They sit in crowded fields where their light blends with the light of other stars. Dust between us and those stars can dim and redden their light in ways that are difficult to correct for perfectly. If the Cepheid measurements were systematically biased, even slightly, it could shift the local value of the Hubble constant downward, closer to the Planck prediction. The tension would dissolve. Lambda CDM would remain intact. No new physics required. This was not a fringe argument. It was a reasonable and widely discussed possibility. The Hubble Space Telescope, while extraordinary, observed primarily in visible and near-infrared light. Its resolution at those wavelengths, roughly 1/10 of an arcsecond, was good, but not perfect. In distant galaxies, individual Cepheids could be blurred together with nearby stars, making them appear brighter than they actually were. If that blending inflated the measured brightness of the Cepheids, it would cause astronomers to underestimate their distances, which would push the calculated expansion rate higher than its true value. The James Webb Space Telescope was built to eliminate exactly this uncertainty. Webb observes at longer infrared wavelengths than Hubble, where dust has less effect on the light. Its mirror is much larger, giving it roughly 4 times the angular resolution of Hubble in the near-infrared. Where Hubble saw a smudge, Webb sees individual stars. Where Hubble struggled to separate a Cepheid from its neighbors, Webb isolates it cleanly. If crowding and blending were biasing the Cepheid distances, Webb would reveal it immediately. In 2023, the SH0ES team conducted the first Webb crosscheck. They observed Cepheids in a nearby galaxy that Hubble had already measured and compared the results. The distances matched. Webb's sharper vision made no meaningful difference to the measurements. The Cepheids were not contaminated by crowding at a level that mattered. Some scientists argued that this initial check was too limited. Maybe the bias only appeared at greater distances, where crowding becomes more severe. Maybe the error was hiding in the farthest galaxies on the ladder, beyond the reach of that first comparison. Fair enough. More data was needed. In 2024, that data arrived. Riess and his collaborators published a comprehensive study using Webb observations of more than 1,000 Cepheid stars across 5 galaxies, extending to NGC 5468, 130 million light-years away. This was the full span of the distance ladder. Every rung checked with Webb's superior instruments. The result was definitive. Hubble's distances and Webb's distances agreed across the entire range, with an average discrepancy of roughly 1/100th of a magnitude. That is an almost negligible difference. The two telescopes were telling the same story. The crowding hypothesis, the last comfortable escape route from the Hubble tension, was ruled out at more than 8 sigma confidence. That is not a gentle disagreement, it is a statistical wall. Freedman-Riess put it plainly. With measurement errors negated, what remains is the real and exciting possibility that we have fundamentally misunderstood the universe. That sentence deserves careful attention. Riess is not a sensationalist. He is one of the most decorated observational cosmologists alive. When he says the universe may be fundamentally misunderstood, he is not reaching for drama. He is describing what the data requires. Not everyone agrees with this framing. And this is where scientific honesty demands nuance. Wendy Freedman, a cosmologist at the University of Chicago and one of the most experienced figures in the field of distance measurements, has pursued independent analyses using Webb data and alternative distance indicators. Her team, the Chicago Carnegie Hubble program, uses not only Cepheids, but also two other types of standard candles, the tip of the red giant branch, known as TRGB, and carbon-rich asymptotic giant branch stars, sometimes called JARG stars. These methods rely on different physics than Cepheids and are therefore affected by different potential systematic errors. In 2025, Freedman's team published updated results incorporating both Hubble and Webb observations across 11 galaxies. Their Hubble constant measurement came in at approximately 70.4 kilometers per second per megaparsec, with an uncertainty of about 3%. This value sits lower than the SH0ES result of 73 and closer to the Planck prediction of 67.4. Freedman has argued publicly that this measurement is consistent with the standard model and does not require new physics. The response from other researchers has been mixed. Dan Skolnick, an astrophysicist at Duke University, noted that Freedman's result lands in the middle of the tension rather than resolving it, and questioned certain choices in her team's supernova sample. At a meeting of the American Astronomical Society in January 2025, Skolnick declared the Hubble tension a crisis. He was not alone. Joe Jensen of Utah Valley University, reviewing a major white paper produced by the Cosmoverse consortium of more than 500 researchers, observed that the vast majority of local measurements cluster around 73, with varying uncertainties. While the early universe prediction remains anchored at 67.4, the TDCOSMO collaboration added yet another independent measurement in late 2025, using a completely different technique. They studied strongly lensed quasars, distant active galactic nuclei whose light is bent and split into multiple images by foreground galaxies. The time delays between the arrival of light along different paths depend on the expansion rate. Using Webb's spectrograph to measure stellar motions in the lensing galaxies, their analysis confirmed a Hubble constant in tension with the Planck value. And in December 2025, the Atacama Cosmology Telescope released its final dataset, nearly 20 years of observations mapping the cosmic microwave background from a mountaintop in Chile. Its results independently confirmed Planck's lower value, reinforcing the early universe side of the disagreement and further tightening the constraints on any model trying to explain the mismatch. So where does this leave us? Two sides of the same measurement, both confirmed by independent instruments and methods, both refusing to budge. The local universe says 73, the early universe says 67. Webb did not resolve the tension. It deepened it, by closing off the most natural explanation for why the two sides disagreed. That alone would be enough to make any cosmologist uncomfortable. But Webb did something else as well. It looked into the early universe and found objects that the standard model did not predict. When astronomers pointed Webb at the deep sky for the first time, they expected to see the cosmic equivalent of a nursery. Tiny, fragile, half-formed galaxies stumbling through their first few 100 million years, still assembling themselves from gas and dark matter through the slow process of gravitational collapse. Lambda CDM predicts that structure formation is hierarchical. Small things form first. They merge into bigger things over time. The earliest galaxies should have been modest, low mass, and still finding their footing. Instead, Webb found giants, In some of the first deep field images, astrophysicist Erica Nelson and her collaborators identified 6 massive galaxy candidates at redshifts between 7 and 10, corresponding to a time when the universe was only about 3 to 5% of its current age. These objects appeared to contain between 10 billion and 100 billion stars each. For context, our own Milky Way contains roughly 200 to 400 billion stars, and it has had 13.8 billion years to assemble them. These galaxies seem to have built comparable stellar populations in a fraction of that time. The team nicknamed them universe breakers. The name was informal, but the concern was real. To build that many stars that quickly, these galaxies would have needed to convert an extraordinarily high fraction of their available gas into stars, far higher than any known physical process seemed to allow. In the Standard Model, star formation is inefficient. Gas collapses, heats up, generates outward pressure, and only a small fraction actually condenses into stars. Feedback from supernovae and active galactic nuclei further limits the rate. Getting even 30 or 40% efficiency is considered optimistic. These early galaxies appeared to require efficiencies approaching or exceeding 80%, which was considered implausible. To appreciate why this shook the community so deeply, you have to understand what astronomers were prepared for versus what they actually saw. The deep field images Webb returned were not subtle. They were not cases where a careful statistical analysis revealed a marginal excess that required a specialist to interpret. The galaxies were right there. Bright red dots scattered across the field, glowing with a confidence that seemed to mock the predictions. Researchers who had spent their careers modeling the first billion years of cosmic history opened their laptops, looked at the data, and saw objects that their simulations said should not yet exist. Not faint hints at the edge of detectability. Objects bold enough to be obvious, sitting in an epoch where the universe was supposed to still be fumbling in the dark. The emotional impact in the community was genuine. For a field accustomed to confirming predictions with ever greater precision, the experience of seeing something profoundly unexpected in the very first batch of deep data was disorienting. It was not the kind of gentle surprise that leads to a minor adjustment in a model parameter. It felt, at least initially, like something fundamental might be off. Headlines erupted. Cosmology was broken. The Big Bang was wrong. The Standard Model was dead. Those headlines were premature. But the underlying observation was genuine, and the scientific community took it seriously. In the years since those initial discoveries, careful follow-up work has resolved part of the puzzle. A study led by University of Texas graduate student Katherine Chworowski, published in 2024, demonstrated that some of the earliest massive galaxy candidates were not as massive as they appeared. Hidden active galactic nuclei, supermassive black holes at the centers of these galaxies, were contributing significant light that was being misattributed to stellar mass. When the black hole contribution was subtracted, the stellar masses dropped substantially. Some of the apparent universe breakers turned out to be more modest systems, inflated by their central engines. Stephen Finkelstein, a co-author of that study, stated clearly that there is no crisis in terms of the Standard Model of cosmology. He emphasized that any theory with Lambda CDM's track record requires overwhelming evidence to overthrow, and the evidence was not there. That was an important correction. But it was not the end of the story. Even after accounting for the black hole contamination, the numbers did not fully return to normal. Chworowski's analysis and subsequent studies found that roughly twice as many massive galaxies remain in Webb's early universe data as the Standard Model predicts. These are not impossible objects. They do not violate the absolute limits set by the amount of matter available in their dark matter halos, but they are uncomfortably abundant. The implication is that star formation in the early universe was more efficient than current models assume. Galaxies in the first billion years after the Big Bang appear to have been better at converting gas into stars than galaxies in the later universe. The physics that governs how gas cools, collapses, and ignites was operating differently or more aggressively, or with fewer of the feedback mechanisms that slow star formation down in the modern cosmos. A separate line of investigation deepened this picture. In 2025, a team led by Lola Danhave at the University of Cambridge used Webb's GRISM mode to study the internal gas motions of more than 250 galaxies between redshifts 4 and 6. What they found was a population of objects that were overwhelmingly turbulent and chaotic. Most of these early galaxies had not settled into the smooth, rotating disks we associate with mature spirals. They were clumpy, disordered systems with gas moving in every direction, merging rapidly, forming stars in violent bursts. Earlier claims of massive, well-ordered disk galaxies at very high redshifts were not confirmed in this larger sample. The picture Danhave's team painted was vivid. Imagine a galaxy not as a serene pinwheel of light, but as a storm. Gas puffed up in every direction, thick clouds colliding and fragmenting, stars igniting in dense knots scattered through the chaos rather than arranged in the graceful spiral arms we know from the nearby universe. These were galaxies still under construction, still figuring out what shape they would become, still digesting the material that was raining into them from the cosmic web. And yet, even in that disorder, they were forming stars at rates that challenged what the physics of gas cooling and gravitational collapse should allow. This result actually helps Lambda CDM in one sense, because the standard model predicts that early galaxies should be messy. But it adds complexity to the picture because the sheer volume of star formation occurring in those chaotic systems still exceeds what the models comfortably produce. The turbulence itself may be part of the answer. Violent collisions between gas clouds can compress material to densities where star formation ignites more readily, bypassing some of the feedback bottlenecks that slow things down in calmer environments. But whether that mechanism alone is enough to explain the observed excess remains an open question. The simulations have not yet caught up with what Webb is showing. The honest summary of where the early galaxy problem stands is this: the initial alarm was too loud, the universe breaker headlines were overblown. Some of the most extreme claims about impossibly massive early galaxies have been walked back as more careful spectroscopy has separated black hole light from starlight. Lambda CDM has not been overthrown by early galaxies, but something is still not fitting neatly. The abundance of massive galaxies in the early universe is higher than predicted. Star formation efficiency appears elevated beyond what standard feedback models produce, and the physical mechanisms responsible for this enhanced early activity are not yet understood. The standard model has not been broken, but it has been stretched. The early universe that Webb reveals is more complex, more productive, and more vigorous than the models anticipated. And here is the detail that turns two separate anomalies into something more troubling. The Hubble tension and the early galaxy problem are both tensions between what the standard model predicts and what observations show. They are different measurements, probing different aspects of the universe at different epochs, but they share a common thread. In both cases, the model's predictions from the early universe do not fully match what we observe. The Planck measurement of the cosmic microwave background gives a Hubble constant of 67.4. That prediction is derived by running the standard model forward from the conditions of the early universe to the present day. The local measurements say the real expansion rate is higher. Something between then and now is not being captured by the model. The Planck-based Lambda CDM model predicts a certain abundance and growth rate for early galaxies. Webb sees more massive galaxies forming faster than that prediction allows. Again, something in the early universe is not behaving the way the standard model expects. These two tensions do not have an obvious shared explanation. No one has published a single theory that cleanly resolves both the Hubble tension and the early galaxy abundance simultaneously, but the pattern is suggestive. When your model's predictions from the early universe disagree with what you measure in the local universe, and separately, the model's predictions for the early universe disagree with what you observe in the early universe, you are no longer dealing with one isolated anomaly. You are looking at a framework that may be missing something about how the universe transitioned from its infant state to its current one. That distinction matters. An isolated anomaly can be a statistical fluctuation, a measurement error, a modeling choice that needs updating. Multiple tensions arising from independent data, probing different epochs, all pointing to the same general direction of disagreement. That is a different kind of signal. It does not prove the model is wrong, but it increases the pressure on anyone trying to maintain that the model is complete, and, as it turns out, these are not the only two directions from which that pressure is building. Because beyond the Hubble tension and beyond the early galaxies, there are other measurements, from other instruments, probing other properties of the universe, that are also pulling away from what Lambda CDM predicts. The picture that emerges when you lay them all side by side is not one of a single crack in a solid wall. It is something wider and more unsettling. It is the possibility that the wall itself may have been built on a foundation that was almost, but not entirely, right. If the Hubble tension were the only problem, cosmologists could treat it as a stubborn measurement puzzle. If the early galaxy abundance were the only surprise, they could adjust their star formation models and move on. What makes the current moment in cosmology genuinely different from previous disagreements is that the pressure is not coming from one direction, it is coming from several. And the instruments delivering that pressure are independent of each other, using different methods, observing different phenomena, probing different epochs of cosmic history. When multiple independent measurements all pull away from the same model in ways that are difficult to reconcile, the conversation shifts. It moves from asking whether a specific observation is wrong to asking whether the model connecting all those observations is missing something. The third tension in this story does not involve the expansion rate at all. It involves something quieter, slower, and in some ways more fundamental. It involves how clumpy the universe is. After the Big Bang, the cosmos was almost perfectly smooth. The cosmic microwave background tells us this directly. The tiny density fluctuations imprinted in that ancient light, variations of 1 part in 100,000, were the seeds from which all structure grew. Over billions of years, gravity pulled matter into denser and denser concentrations. Gas fell into dark matter halos, stars formed, galaxies assembled, clusters collected into the filaments and walls of the cosmic web. The universe went from nearly uniform to spectacularly lumpy. The rate at which that lumpiness grew is one of the most important predictions the standard model makes. Lambda CDM takes the initial conditions measured by Planck, applies the known laws of gravity and the known properties of dark matter and dark energy, and calculates exactly how much cosmic structure should exist at every subsequent epoch. The result is expressed as a parameter called SATE. It quantifies how much matter has clumped together on scales of roughly 26 million light-years by the present day. A higher SATE means more clumping. A lower SATE means less. Planck's measurement of the cosmic microwave background, combined with the standard model, predicts a specific value of SATE. That prediction says the universe today should be clumped to a particular degree, based on how the initial fluctuations should have grown under the influence of gravity, dark matter, and dark energy over 13.8 billion years. When astronomers go out and measure the actual clumpiness of the nearby universe, they get a different number. The measured SATE is consistently lower than the predicted value. The nearby universe is smoother than it should be. Matter has not clumped as aggressively as the standard model says it should have. The primary technique used to make this measurement is called weak gravitational lensing, and it deserves a moment of explanation because it is one of the most elegant methods in all of observational cosmology. Einstein's general relativity tells us that mass bends the path of light. A massive object sitting between you and a distant source will curve the light from that source, distorting its apparent shape. When the foreground mass is something enormous and compact, like a galaxy cluster, the distortion is dramatic. Background galaxies are stretched into arcs and rings, visible in telescope images. That is strong lensing, and it produces effects you can see by eye. Weak lensing is the subtle cousin of that process. Instead of a single massive cluster bending the light from a single background galaxy, imagine all the dark matter distributed across hundreds of millions of light years, the sheets and filaments and halos of the cosmic web, each contributing a tiny gravitational tug on the light passing through. No single structure distorts a background galaxy enough to notice, but across millions of galaxies, a statistical pattern emerges. Galaxies that should have random orientations begin to show a slight preferential alignment, a coherent stretching imprinted by the gravitational field of all the matter between them and us. By measuring those tiny correlated distortions across vast stretches of sky, astronomers can reconstruct the distribution of all the matter in the foreground, including the dark matter that emits no light. The stronger the distortions, the more clumped the matter is. The weaker the distortions, the smoother the distribution. It is, in effect, using the shapes of distant galaxies as a screen onto which the entire three-dimensional matter distribution of the cosmos is projected. The measurement is extraordinarily difficult. The distortions are small, typically changing a galaxy's shape by about 1%. Galaxies already have intrinsic shapes that vary enormously, so the lensing signal is buried under a mountain of natural variation. Extracting it requires averaging over millions of galaxies and correcting for every possible systematic effect, from the way the telescope's optics distort images, to the way Earth's atmosphere blurs them, to the way the software measures galaxy shapes in the first place. It is painstaking, meticulous work. And when different teams do it independently, using different telescopes and different analysis methods, the results broadly agree. The universe is less clumpy than Lambda CDM predicts. This is the SATE tension, and it has been building for years across multiple independent surveys. The Kilo-degree survey, known as KIDS, has been one of the leading programs investigating this discrepancy. Using data from the VLT survey telescope in Chile, KIDS measured the weak lensing signal across hundreds of square degrees of sky and found an SATE value roughly 8% lower than the Planck prediction. The statistical significance of this offset has fluctuated across different data releases and analysis choices, typically sitting between 2 and 3 sigma. That is not as dramatic as the 5 sigma Hubble tension, but it is persistent, and it refuses to go away. The Dark Energy Survey, using the Blanco telescope in Chile, found similar results. The Hyper Suprime Cam survey, conducted with the Subaru telescope in Hawaii, published updated results in 2025 that also confirmed a lower SATE value than the standard model predicts. A study specifically examining whether messy galactic processes like gas, heating, and feedback could explain the discrepancy concluded that they could not fully account for it. Not every survey finds a strong tension. The KIDS legacy analysis, the final data release from that survey, reported results somewhat closer to the Planck prediction than earlier releases, leading some researchers to suggest the SATE tension might be weakening. And the Dark Energy Spectroscopic Instrument, using a different approach based on galaxy clustering rather than weak lensing, found an SATE value broadly consistent with Planck when analyzing its full galaxy sample. But when the DESI team looked more carefully at specific galaxy populations at specific epochs, the picture became more interesting. Tanveer Karim and collaborators examined emission-line galaxies at a redshift of roughly 1.1, corresponding to light emitted roughly 8 billion years ago, when the universe was less than 6 billion years old. These are small, actively star-forming galaxies similar in mass to our Milky Way. In that population, the SATE tension reappeared. The clumpiness was lower than the standard model predicted, and it was already present at an epoch when, according to Lambda CDM, dark energy should not yet have been significantly influencing structure growth. That last detail is important. The SATE tension was initially assumed to be a late universe effect, something related to how dark energy suppresses the growth of structure in the recent cosmic past. If the discrepancy is already present at earlier times, before dark energy became dominant, then the simple explanation of a cosmological constant doing its expected work does not fully account for the observed smoothness. Something else may be happening. The SATE tension is milder than the Hubble tension. It has not reached the 5 sigma threshold that would demand immediate revision of the model, and there are legitimate concerns about systematic effects in weak lensing measurements, from the modeling of galaxy shapes to the calibration of photometric redshifts to the impact of Milky Way dust on the observed galaxy distribution. Karim's own work showed that the choice of dust correction map can shift the inferred SATE value, highlighting how sensitive these measurements are to analysis choices, but the pattern matters. When you step back and look at the landscape, the Hubble constant is higher locally than the early universe predicts. The growth of structure is lower locally than the early universe predicts. Both tensions point in the same conceptual direction. The model's extrapolation from the infant universe to the present universe overshoots in some places and undershoots in others. Something about how the universe evolved between those two epochs is not fully captured by Lambda CDM's 6 parameters. And then, in March of 2025, a completely different instrument delivered results that added yet another layer of pressure. The Dark Energy Spectroscopic Instrument sits on the Nicholas U. Mayall 4-meter telescope at Kitt Peak National Observatory in Arizona. It is not a telescope that takes pretty pictures. It is a machine built to do one thing extraordinarily well: measure the positions and distances of millions of galaxies and quasars across billions of light years, building the largest 3-dimensional map of the universe ever created. That map allows researchers to measure baryon acoustic oscillations, the fossilized sound waves from the early universe imprinted on the distribution of galaxies, with a precision that surpasses anything achieved before. Baryon acoustic oscillations serve as a standard ruler. Their characteristic scale, roughly 500 million light-years in today's universe, was set by the physics of the early cosmos and has been expanding with space ever since. By measuring how that ruler appears at different distances and therefore at different epochs, DESI can track the expansion history of the universe with extraordinary precision. It is one of the cleanest ways to study how dark energy has behaved over the last 11 billion years. In its first data release, based on the initial year of observations, DESI had already hinted at something unexpected. When its measurements were combined with data from the cosmic microwave background and supernova surveys, the best fit was not a cosmological constant. The data preferred a model in which dark energy's influence changes over time. Specifically, it hinted that dark energy may be weakening, becoming less dominant as the universe ages. That result was intriguing but preliminary. Many 3 sigma signals in physics have faded with additional data. The cosmological community watched and waited. In March 2025, DESI released its second round of results, incorporating the first 3 years of its main survey. The signal did not fade. It strengthened. When DESI's baryon acoustic oscillation measurements were combined with cosmic microwave background data from Planck and with different supernova datasets, the preference for evolving dark energy ranged between 2.8 and 4.2 sigma, depending on the specific combination of data used. The standard Lambda CDM model, in which dark energy is a fixed cosmological constant with an equation of state parameter of exactly -1, struggled to simultaneously fit all the datasets. A model in which that parameter evolves with time, starting more negative than -1 in the past and moving toward less negative values in the present, provided a consistently better fit. To understand what that means physically, imagine dark energy as a kind of pressure woven into the fabric of space. In Lambda CDM, that pressure is fixed. Every cubic meter of space pushes outward with exactly the same force today as it did 5 billion years ago and as it will 5 billion years from now. The cosmological constant never changes. It is a permanent feature of space-time, constant in density, even as the universe expands. If DESI's hints are correct, then this picture is wrong. Dark energy is not a fixed property of space. It is a dynamic field, something that has its own history, its own evolution, its own trajectory over cosmic time. In the past, when the universe was younger and smaller, dark energy may have pushed harder. Today, its grip may be loosening. The accelerating expansion of the universe, the defining discovery of modern cosmology, may itself be changing character. The implications of that possibility are staggering. If dark energy is weakening, the acceleration it drives will eventually slow. In the most extreme versions of evolving dark energy models, the acceleration could stop altogether. The universe, instead of expanding forever into cold emptiness, could enter a new phase. Not a recollapse, but a deceleration, a gradual settling into a different kind of future than the one Lambda CDM predicts. The fate of the cosmos itself, the question of whether everything ends in ice or something else, hinges on whether DESI's signal is real. Willem Elbers, co-chair of DESI's Cosmological Parameter Estimation Working Group, described the situation clearly. For a couple of decades, we have had this standard model of cosmology that is really impressive. As our data are getting more and more precise, we are finding potential cracks in the model and realizing we may need something new to explain all the results together. Will Percival, co-spokesperson for DESI, was more direct. The simplest explanation for what we see is shifting. It is looking more and more like we may need to modify our standard model of cosmology to make these different datasets make sense together, and evolving dark energy seems promising. Now, an essential caution. The DESI results have not crossed the 5 sigma threshold. They are not a discovery. They are a hint, a strong and growing hint, but a hint nonetheless. Many signals at 3 or even 4 sigma have vanished with more data in the history of physics. The DESI collaboration itself has been careful to note this. Their analysis used blinding techniques to prevent unconscious bias, and they have subjected their results to extensive systematic checks. But they are not claiming to have overthrown Lambda CDM. They are saying the data prefers something beyond it. The response from the broader community has been a mixture of excitement and caution. Some researchers have embraced the evolving dark energy interpretation. Others have pointed out that the preference for time-varying dark energy depends heavily on which supernova dataset is used in the combination, and that internal tensions between the different datasets complicate the interpretation. A paper published in the European Physical Journal C in late 2025 argued that the DESI claim of dynamical dark energy is not entirely robust because of these inter-dataset tensions, while simultaneously noting that when each dataset is analyzed independently, the preference for evolving dark energy over a cosmological constant is actually quite strong. This is how frontier science works. The signal is there, the interpretation is being debated, the data will improve. DESI is continuing to observe, and future releases will either strengthen or dissolve the hint. But for the moment, the hint exists, and it points in a direction that would require modifying the lambda in Lambda CDM. The cosmological constant, the simplest possible description of dark energy, may not be the right one. And here is where the threads begin to weave together into something larger, not in a neat, clean way, not with a single equation that resolves everything at once, but in the way that matters most to working scientists. As a pattern, consider what the three tensions look like when you lay them side by side. The Hubble tension says the universe is expanding faster locally than the standard model predicts from early universe data. The prediction starts at the cosmic microwave background and runs forward through 13.8 billion years of modeled evolution. Somewhere along that chain, the prediction and the measurement diverge. The local universe is doing something the model did not anticipate. The SAT tension says the universe is less clumpy locally than the standard model predicts from the same early universe data. The same starting conditions, run through the same model, produce a different kind of mismatch. The local universe is smoother than it should be. Structure has not grown as aggressively as the equations demanded. The DESI results suggest that dark energy, the force governing the expansion and influencing the growth of structure, may not behave the way the model assumes. If dark energy is evolving, it changes both how fast space stretches and how effectively gravity can pull matter together against that stretching. It touches both the expansion rate and the clumpiness simultaneously. Each of these tensions has its own data, its own instruments, its own community of specialists. They were not discovered by the same team or measured with the same telescope. They emerged independently from different corners of observational cosmology, and yet they share a structural feature that is difficult to dismiss as coincidence. In every case, the disagreement is between what the early universe tells us should be happening and what the late universe shows us is actually happening. The model's forward projection from its exquisitely measured starting point does not land where the instruments say it should. That convergence is the heart of the matter. One tension is a puzzle. Two tensions are a concern. Three tensions, all pointing in the same conceptual direction, all revealing a gap between the model's extrapolation and the observed reality, begin to look like a signal. Not a signal of what the answer is, but a signal that there is an answer to find. Researchers have proposed dozens of theoretical fixes. Some add energy to the early universe. Some modify the properties of dark matter. Some introduce new interactions between dark matter and dark energy. Some let the cosmological constant evolve. The proposals are creative, diverse, and in many cases, mathematically rigorous. But they share a common frustration. Each one can address one tension, sometimes two. None has yet been shown to resolve all of them simultaneously without creating new problems elsewhere. The modifications that help the expansion rate tend to worsen the structure growth. The adjustments that smooth out the clumpiness tend to conflict with the expansion history, and the models that let dark energy evolve are not yet constrained enough by the data to identify a unique solution. Every proposed patch pulls on a different thread, and pulling on one thread tightens another. That pattern is itself informative. It suggests that whatever the model is missing, is not a minor tweak that can be applied in one place without disturbing the rest of the framework. It is something more fundamental, something woven into the structure of the model itself. That diagnostic matters more than any individual proposed fix. When a single anomaly appears in a single dataset, the most likely explanation is usually mundane: a calibration error, an overlooked systematic, a statistical fluctuation that will fade with more data. When multiple anomalies appear simultaneously from independent datasets, and when attempts to resolve one reliably disturb another, the situation changes. The problem is unlikely to be local. It is unlikely to be a matter of one team making one mistake in one analysis pipeline. The interconnection of the tensions suggests that whatever is missing from the model sits deep enough in the framework that its effects ripple outward into multiple observables at once. That is not a flaw that can be patched at the surface. It points towards something structural, something embedded in the assumptions that connect the model's starting conditions to its predictions, not in the details of any single measurement. In September of 2025, the Tensions in Cosmology conference brought together more than 130 researchers in Corfu, Greece, specifically to take stock of exactly this situation. The conference was not a routine academic gathering. It was convened because the community recognized that the number of simultaneous tensions had reached a point where coordinated assessment was necessary. Researchers presented the latest data on the Hubble constant, the SATE parameter, and the growing list of emerging anomalies from DESI, Webb, the Atacama Cosmology Telescope, Planck, and other facilities. They debated the merits and failures of competing theoretical proposals. They examined whether the different tensions might share a common origin or whether they are genuinely independent problems requiring independent solutions. The resulting meeting report, published in Nature Astronomy in early 2026, did not declare a winner among the proposed models. It could not. No proposal had earned that status. The tone of that report was measured but unmistakable. The standard model is under more simultaneous pressure than at any previous point in its history. The tensions are not converging toward resolution. They are, if anything, becoming more clearly defined as the data improves, and the theoretical landscape for explaining them remains fragmented, with the community still searching for the single insight that might bring coherence to the picture. It is worth pausing to appreciate what this means structurally. Lambda CDM is a model with 6 parameters that has explained an enormous range of observations for more than 2 decades. It is not being challenged by one rogue measurement or one speculative theoretical idea. It is being pressed from at least 3 independent observational directions simultaneously. The expansion rate is too high locally. The cosmic structure is too smooth locally. Dark energy may not be constant. Each of these tensions has its own dataset, its own measurement techniques, its own systematic uncertainties, and its own community of researchers working to confirm or refute it. They are not the same measurement being done 3 times. They are 3 different measurements, probing 3 different properties of the universe, all arriving at answers that do not sit comfortably within the standard framework. When a model faces pressure from a single direction, the standard scientific response is to look for a systematic error or a minor adjustment that brings the model back into agreement. That approach has been tried for the Hubble tension for nearly a decade. It has not succeeded. Webb's confirmation of the local distance ladder has made it significantly harder. When a model faces pressure from multiple independent directions simultaneously, the conversation begins to shift. Researchers start asking not how to fix one measurement, but whether the model itself is missing an ingredient, whether its 6 parameters, as successful as they have been, are not quite enough to describe the universe at the level of precision now being achieved. What makes this moment distinctive in the history of cosmology is the combination of observational pressure and theoretical uncertainty. The data is better than it has ever been. Webb's infrared vision has confirmed the distance ladder to unprecedented precision. Planck's cosmic microwave background map remains the gold standard for early universe measurements. DESI's three-dimensional galaxy map is the most detailed ever constructed. The Atacama Cosmology Telescope's final data release has provided an independent confirmation of the early universe expansion rate. Weak lensing surveys are mapping the distribution of dark matter across hundreds of millions of galaxies. All of these datasets are excellent. All of them are well calibrated and extensively tested for systematic errors. And when you try to fit all of them simultaneously with a single 6-parameter model, the fit is not as good as it used to be. Not catastrophically bad, Lambda CDM still provides a reasonable description of the universe, but the residuals are growing. The tensions between datasets are becoming harder to dismiss as statistical noise or uncorrected systematics. The model is not collapsing, but it is being squeezed. There is an analogy that physicists sometimes use in situations like this. Imagine a map of a continent drawn by an explorer centuries ago. The map is remarkably accurate. The coastlines are right, the major rivers are in the correct positions, the mountain ranges follow the right trajectories. For decades, everyone uses the map, and it serves them well. Then, someone invents a satellite and takes a photograph from orbit. The photograph confirms most of what the map shows. The coastlines really are where the explorer drew them. The rivers really do flow where the map says. But in a few places, small but definite, the map does not match the photograph. A bay that is not on the map, a peninsula that is slightly longer than drawn, a mountain range that curves where the map says it is straight. The map is not wrong. It is extraordinarily good, but it is not complete. And the satellite, by seeing with greater clarity than the explorer ever could, has revealed the places where the map's accuracy ends. Webb, Planck, DESI, and the lensing surveys are the satellite. Lambda CDM is the map, and the places where the map stops matching the photograph are the Hubble tension, the Sate tension, and the hints of evolving dark energy. The question now is what lies in those gaps. What physics, not yet included in the 6 parameters, might account for what the satellite sees and the map does not show? And the deepest version of that question, the one that reaches beyond any individual tension or measurement, is whether the universe is trying to tell us something about the nature of dark energy, the behavior of dark matter, or the laws of gravity on the largest scales that we have not yet been willing to hear. What makes this uncertainty different from the many previous disagreements in cosmology that eventually dissolved is the quality of the data on both sides. In the past, when a measurement conflicted with a prediction, the most common resolution was that the measurement improved and the disagreement went away. Better telescopes, larger samples, more careful calibrations, and the anomaly would shrink until it vanished into the noise. That pattern has defined the history of precision cosmology for decades. Tension appears, instruments improve. Tension disappears, model survives. What is happening now is the opposite. The instruments have improved, in some cases by factors that would have been unimaginable a generation ago, and the tensions have not disappeared. In several cases they have sharpened. The normal cycle of measure, refine, resolve is not completing. The data is getting better and the disagreements are getting clearer, and that combination is what separates a genuine anomaly from a transient one. Scientists who have spent entire careers watching discrepancies dissolve under better data are now watching these ones refuse to dissolve. That is not proof that the model is wrong. But it is the reason the conversation has shifted from whether there might be a problem to what the problem might be. The instruments are listening, the data is accumulating. And the model that has served cosmology so faithfully for more than 2 decades is, for the first time, genuinely struggling to keep up with what the universe is showing us, not failing, not collapsing, but straining at the seams in ways it never had to before. And the next question, the one that matters most, is what happens when a model that has worked for 2 decades begins to creak under the weight of its own success. When the instruments built to celebrate it start to challenge it instead. That question has not been answered. But the pressure that will force an answer is building from every direction at once. There is a moment in the history of every great scientific framework when it stops being questioned by outsiders and starts being questioned by the Kamfa, people who built it. That moment does not arrive because the framework has been proven wrong. It arrives because the framework has been tested so precisely, with instruments so sharp and datasets so large, that the places where it stops working become impossible to ignore. The framework does not collapse in that moment. It does something more interesting. It reveals its own edges. We have been here before. In the late 19th century, physics appeared to be nearly complete. Classical mechanics, built on the foundations laid by Isaac Newton more than 200 years earlier, could describe the motion of everything from falling apples to orbiting planets with extraordinary accuracy. James Clerk Maxwell had unified electricity and magnetism into a single, elegant theory. Thermodynamics described the behavior of heat and energy with precision. The prevailing sentiment among many physicists was that the fundamental laws of nature were essentially known, and all that remained was to refine the measurements. Then the measurements got better. In 1887, Albert Michelson and Edward Morley conducted an experiment designed to detect the motion of Earth through the luminiferous ether, the invisible medium that was assumed to carry light waves through space. The experiment found nothing. The ether did not exist. Light did not need a medium to travel through. That null result, a measurement that refused to match what the theory predicted, became one of the first cracks in the classical picture. A few years later, observations of the orbit of Mercury revealed a tiny anomaly. The point of Mercury's closest approach to the Sun was shifting, precessing, by an amount that Newtonian gravity could not fully explain. The discrepancy was small, roughly 43 arcseconds per century, almost nothing. But it was real, and no adjustment to Newton's framework could account for it without introducing ad hoc assumptions that had no independent justification. Neither of these anomalies destroyed classical physics overnight. Newton's laws continued to work beautifully for the vast majority of situations. Bridges still stood. Satellites could still be launched. The motion of every planet except Mercury was still described with stunning accuracy. The framework was not wrong. It was incomplete. It was an approximation that worked extraordinarily well within certain limits, but broke down at the edges, in the domain of very high velocities and very strong gravitational fields. The resolution came in 1915, when Einstein published his general theory of relativity. It did not discard Newton's work, it encompassed it. Newtonian gravity became a special case within a deeper and more general framework, accurate in the regimes where Newton had tested it and extended into the regimes where it failed. Mercury's orbit was explained. The behavior of light in gravitational fields was predicted and confirmed. The expansion of the universe itself became a consequence of the equations. This is how scientific revolutions actually work. Not through demolition, but through deepening. The old framework does not become useless. It becomes a limiting case of something more complete. And the anomalies that signaled the transition, The small but stubborn disagreements between prediction and observation turned out not to be errors. They were clues. Lambda CDM may be approaching a similar threshold. That statement requires care. It is not a declaration that the standard model has failed. As of this moment, Lambda CDM remains the most successful cosmological framework ever constructed. It explains the cosmic microwave background with breathtaking precision. It predicts the large-scale distribution of galaxies. It describes the expansion history of the universe across billions of years. Its 6 parameters provide a coherent, quantitative description of the observable cosmos that no alternative model has come close to matching in overall explanatory power. But the anomalies are accumulating. The Hubble tension has survived the sharpest observational test ever applied to it. The SATE tension persists across multiple independent surveys. DESI's baryon acoustic oscillation measurements hint that dark energy may be evolving rather than sitting as a fixed constant. And Webb's observations of the early universe reveal a cosmos that was building structure faster and more vigorously than the standard timeline predicted. Each of these tensions is individually debatable. Taken together, they form a pattern that is increasingly difficult to dismiss. The pattern is this. When you use the standard model to extrapolate from the conditions of the early universe to the present day, the predictions do not quite match the observations. The expansion rate comes out too low. The cosmic structure comes out too clumpy. The assumed constancy of dark energy may not be justified. The abundance of early galaxies exceeds what the models produce. In every case, the disagreement is between what the model calculates and what the instruments measure. And in every case, better instruments have sharpened the disagreement rather than resolving it. This is precisely the signature that preceded the transition from Newtonian gravity to general relativity. The old framework was not producing wrong answers in most regimes. It was producing slightly wrong answers in specific regimes. And those slight errors were being revealed by increasingly precise measurements. Understanding what it would mean for the standard model to be incomplete requires thinking carefully about what the standard model actually assumes. Lambda CDM rests on 3 foundational pillars. The first is general relativity, which governs how matter and energy curve space-time and how that curvature determines the motion of everything in the universe. The second is the cosmological principle, the assumption that on the largest scales, the universe is homogeneous and isotropic, meaning it looks essentially the same in every direction and from every location. The third is the specific content of the universe, described by those 6 parameters, which includes the densities of ordinary matter, dark matter, and dark energy, plus the amplitude and spectrum of the initial fluctuations. Each of these pillars could, in principle, be the source of the problem. If general relativity does not behave exactly as expected on cosmological scales, the expansion history and structure growth would be different from what the model predicts. If the cosmological principle is not perfectly satisfied, meaning the universe has large-scale inhomogeneities or preferred directions that we have not accounted for, the measurements could be subtly biased in ways that mimic a tension with the model. And if the content of the universe includes components or behaviors not captured by the 6 parameters, such as evolving dark energy, interacting dark matter, or additional particle species, the model's predictions would shift. Researchers are actively investigating all 3 possibilities. Modified gravity theories attempt to extend general relativity in ways that preserve its successes while altering its behavior on the largest scales. Proposals like FR gravity and scalar tensor theories have been studied for decades within the theoretical physics community, and some can address specific tensions. But the constraints from gravitational wave observations, galaxy cluster dynamics, and the cosmic microwave background are severe. Any modification must be extremely subtle to avoid conflicting with the mountain of data that general relativity already explains. Violations of the cosmological principle are harder to test directly, but they have been explored, and the idea is more intuitive than it sounds. The cosmological principle says that no location in the universe is special. On sufficiently large scales, the density of matter is the same everywhere. There are no preferred directions, no cosmic center, no privileged vantage point. The universe, when you zoom out far enough, is smooth. But what if it is not perfectly smooth at the scales that matter for our measurements? What if the particular patch of the universe we inhabit happens to be slightly less dense than the cosmic average? Not dramatically less dense, not a void in the conventional sense, just a region, perhaps a few 100 million light-years across, where there is fractionally less matter pulling inward than the global mean. If we lived inside such a region, the consequences would be subtle but real. With less matter nearby to gravitationally slow the local expansion, space in our neighborhood would be stretching slightly faster than the universal average. When we measure the Hubble constant using Cepheids and supernovae in our cosmic vicinity, we would get a number that is slightly too high, not because the universe as a whole is expanding that fast, but because our particular corner of it is. The Planck value, derived from the cosmic microwave background, represents the true global average. The local measurement represents our slightly atypical neighborhood. The tension between the two would not require any new physics at all, just an accident of address. The idea has a certain elegance. It would explain the Hubble tension without modifying gravity, without inventing new particles, without changing the nature of dark energy. It would simply mean that the universe is a little lumpier on large scales than the cosmological principle assumes, and we happen to live in one of the lumps. Or rather, in one of the gaps between lumps. However, most analyses suggest that the density contrast required to fully explain the Hubble tension would need to be implausibly large, significantly bigger than what galaxy surveys observe in our vicinity, and the isotropy of the cosmic microwave background places tight limits on how inhomogeneous the universe can be on the relevant scales. A local void, large enough and deep enough to account for the full 6 km per second per megaparsec gap between 73 and 67, would leave a signature in the microwave background that Planck should have detected. It did not. The idea remains on the table as a partial contributor, but it cannot carry the full weight of the tension on its own. The third possibility, that the contents of the universe are more complex than 6 parameters capture, is where most of the theoretical activity is concentrated. Early dark energy is one example. It proposes that a brief episode of additional dark energy in the first 100,000 years or so after the Big Bang changed the expansion rate enough to alter the sound horizon, the characteristic scale imprinted in the baryon acoustic oscillations, which in turn changes the Hubble constant inferred from the cosmic microwave background. Some versions of early dark energy can reduce the Hubble tension significantly, but they tend to affect the cosmic microwave background power spectrum in ways that degrade the fit to Planck data, and they often exacerbate the SAT tension. Evolving dark energy, the scenario suggested by DESI's measurements, does not require a sudden early episode. Instead, it proposes that the equation of state of dark energy, the parameter that describes how its pressure relates to its energy density, is not a fixed constant, but varies smoothly over cosmic time. If dark energy was stronger in the past and has been weakening, the expansion history would differ from the Lambda CDM prediction in ways that could simultaneously affect the Hubble measurement and the growth of structure. The challenge is finding a specific form of evolution that fits all the available data, and as the analyses from DESI and independent groups show, The current datasets are not yet constraining enough to uniquely identify the correct model. There are more exotic proposals as well. Some researchers have investigated whether dark matter might have properties beyond simple, cold, collisionless particles. If dark matter interacts with itself, with dark energy, or with ordinary matter through forces not yet detected, it could alter the growth of structure in ways that address the SATE tension. Others have explored the possibility that the universe contains additional light particle species, sometimes called dark radiation, which would change the expansion rate in the early universe and affect the inferred Hubble constant. None of these proposals has achieved consensus. The landscape is populated by dozens of competing models, each capable of addressing one or two tensions, but typically struggling with the others. This is the hallmark of a field that has identified a real problem, but has not yet found its solution. The anomalies are defined, the existing framework is understood. The space of possible extensions is being systematically explored. What is missing is the single insight, the one modification or addition that brings everything back into agreement. It is tempting to find this situation frustrating. Science, in the popular imagination, progresses through dramatic breakthroughs. An old theory is overthrown, a new one takes its place. The textbooks are rewritten overnight. In practice, the transitions are slower and messier. The period between the identification of anomalies and the emergence of a new framework can last decades. The anomalies in Newtonian gravity accumulated over several decades before Einstein provided the resolution. The ultraviolet catastrophe in classical radiation theory persisted for years before Planck's quantum hypothesis explained it. The neutrino mass puzzle took more than 20 years to resolve. Cosmology may be in an analogous transitional period right now. The anomalies are defined. The data is accumulating. The theoretical community is actively searching, but the resolution has not yet appeared. What makes this particular transition unique in the history of physics is the role of observational technology. Previous transitions were often triggered by single experiments or observations, a solar eclipse confirming the bending of starlight, the photoelectric effect defying classical predictions. The current cosmological tensions are being driven by a suite of instruments operating simultaneously, each probing a different aspect of the universe, each delivering data of unprecedented quality. The James Webb Space Telescope is the most prominent member of this suite, but it is far from the only one. And the instruments that are coming online over the next several years are not incremental upgrades. They are purpose-built machines designed to attack exactly the questions this story has been building toward. DESI is continuing to map the expansion history with millions of galaxy spectra, and its future data releases will either strengthen or dissolve the hints of evolving dark energy. The Atacama Cosmology Telescope and the South Pole Telescope have provided independent measurements of the cosmic microwave background that will be extended by the upcoming Simons Observatory and eventually by the proposed CMB-S4 project, which aims to map the microwave background with a sensitivity that dwarfs anything currently available. The Euclid satellite, launched by the European Space Agency in 2023, is surveying more than a third of the sky in both visible and near-infrared light. Its primary mission is to map the distribution of galaxies and the subtle distortions caused by weak gravitational lensing across a volume of space far larger than any ground-based survey has covered. Euclid's lensing measurements will provide one of the most powerful independent tests of the SATE tension, because the satellite observes above the atmosphere, eliminating the blurring that complicates ground-based galaxy shape measurements. Its first major cosmological results, expected in 2026, will either confirm or challenge the low SATE values reported by KEEDS, the Dark Energy Survey, and the Hyper-Suprime CAM program, the Vera-C. Rubin Observatory in Chile is preparing to conduct the Legacy Survey of Space and Time, an unprecedented 10-year optical survey that will image the entire accessible sky every few nights. When fully operational, Rubin will discover and track thousands of Type Ia supernovae per year, compared to the hundreds that current surveys manage. That flood of standardized distance measurements will constrain the expansion history with a statistical power that makes current supernova datasets look like pilot studies. Rubin will also measure weak lensing across billions of galaxies, providing an independent check on the SATE parameter with a precision that should resolve whether the tension is real or an artifact of current survey limitations. And NASA's Nancy Grace Roman Space Telescope, expected to launch before the end of this decade, combines the wide-field survey power of a ground-based observatory with the sharpness and stability of a space telescope. Roman will measure both supernovae and galaxy shapes across enormous volumes of space, probing the expansion history and the growth of structure simultaneously. It is specifically designed to study dark energy's behavior using multiple independent methods within a single instrument. If dark energy is evolving in the way DESI's hints suggest, Roman should see it clearly. If it is not, Roman will set the tightest constraints ever achieved on how constant the cosmological constant truly is. Each of these instruments attacks the problem from a different angle. If the tensions are real, meaning they reflect genuine incompleteness in the standard model rather than measurement errors, then, as these instruments deliver their data over the next decade, the tensions should become sharper and more clearly defined. The statistical significance should grow, the systematic uncertainties should shrink, and the space of viable theoretical alternatives should narrow. If, on the other hand, the tensions turn out to be the product of subtle measurement biases, instrument calibration issues, or analysis choices that were not fully understood, then the new data should reveal those problems and the tensions should dissolve. That outcome is entirely possible and would represent its own kind of scientific triumph, a demonstration that the standard model is even more robust than it appeared. Either way, the next decade will be decisive. The data that is coming will either confirm that Lambda CDM needs modification or vindicate it against the strongest challenge it has ever faced. There is no third option. The instruments are too precise, and the questions are too well defined for the answer to remain ambiguous indefinitely. There is something important to say about what is not happening in this story, because the public narrative around these tensions has frequently been misleading. The Big Bang has not been disproven. The universe is not collapsing. Scientists are not panicking. The foundational observation that the universe began in a hot, dense state roughly 13.8 billion years ago and has been expanding and cooling ever since is not challenged by any of the tensions described in this story. The cosmic microwave background remains one of the most precisely confirmed predictions in all of science. The existence of dark matter is supported by multiple independent lines of evidence, from galaxy rotation curves to gravitational lensing to the acoustic peaks in the microwave background. The existence of dark energy, in some form, is required by the observed acceleration of the expansion. What is being questioned is not whether these things exist, but whether the simplest possible description of how they behave is fully accurate. Lambda CDM assumes dark energy is a cosmological constant. It might not be. Lambda CDM assumes dark matter is cold and collisionless. It might have additional properties. Lambda CDM assumes general relativity is perfectly accurate on all scales. It might need extension in certain regimes. These are refinements within a broadly successful framework, not repudiations of the framework itself. The distinction matters because the public conversation about cosmology often treats any tension as evidence that everything is wrong, that scientists have been deceived, or that the entire enterprise of cosmological modeling is misguided. That reading misunderstands how science works. Models are not permanent truths. They are the best available descriptions of nature at a given level of observational precision. When the precision improves and the model stops fitting, the model is not discredited, it is promoted. It has graduated from a working description to a limiting case within something deeper. That is what may be happening to Lambda CDM. And if it is, then this period, the early decades of the 21st century, will be remembered as the era when the instruments became sharp enough to see the edges of one of science's greatest achievements and to begin the search for what lies beyond those edges. James Webb did not cause this situation. The tensions existed before Webb launched. The Hubble tension was identified in the mid-2010 era. The SATE tension has been building for a decade. The possibility of evolving dark energy has been discussed theoretically for even longer. What Webb did was remove the ambiguity. By confirming the distance ladder with its superior infrared vision, Webb closed the door on the most comfortable explanation for the Hubble tension. By revealing the unexpectedly vigorous early universe, Webb demonstrated that the Standard Model's predictions for structure formation were not matching reality at the earliest accessible epochs. By providing data of such quality that the measurement errors are no longer large enough to hide behind, Webb forced the field to confront the possibility that the remaining discrepancy is not a problem with the measurements. It is a problem with the model. That is a profoundly important scientific contribution, not because it answers the question, but because it establishes that the question is real. Before Webb, it was possible to hope that the Hubble tension was an artifact of crowded star fields and dusty sightlines. After Webb, that hope has been tested and found insufficient. Before Webb, the early galaxy problem could be dismissed as premature claims based on photometric estimates that had not been confirmed spectroscopically. After Webb, extensive spectroscopic follow-up has resolved part of the puzzle but left a meaningful residual that demands explanation. Before Webb, the conversation about the Standard Model's completeness was theoretical. After Webb, it is observational. There is a phrase that researchers in this field use when describing the current situation. They call it a crisis of precision. The word crisis, in this context, does not mean catastrophe. It means a decision point, a moment where the data has reached a level of quality that forces a choice. Either the model is correct and some undiscovered systematic error is responsible for the tensions, or the model is incomplete and the tensions are the first glimpses of whatever comes next. That framing captures something essential about the scientific process. Progress does not come from models that always work. Progress comes from models that work almost perfectly, because the places where they fail are the places where new physics hides. If Lambda CDM were a rough approximation that only vaguely matched the data, its failures would not be informative. They would just be failures. But because Lambda CDM is extraordinarily precise, its failures are extraordinarily informative. Each tension is a clue. Each disagreement between prediction and observation is a signpost pointing toward whatever the model is missing. The Hubble tension tells us that something about the relationship between the early and late universe is not fully described by 6 parameters and a cosmological constant. The SATE tension tells us that the growth of structure over cosmic time may involve physics not captured in the current framework. The DESI hints tell us that dark energy, the dominant component of the universe, may be more complex than a single fixed number. And Webb's early galaxies tell us that the universe's first billion years were more productive and more turbulent than the standard timeline predicted. These are not random complaints about an otherwise perfect model. They are specific, quantifiable, observationally grounded signals that something is missing. And the fact that they all point in the same general direction, toward a universe that evolved differently between the early and late epochs than Lambda CDM predicts, suggests that whatever is missing may be a single deeper principle rather than a collection of unrelated patches. Finding that principle is the task of the next generation of cosmologists. The instruments are in place or are being built, the data is flowing, the theoretical community is engaged. The history of physics suggests that when anomalies of this quality accumulate around a successful framework, the resolution, when it comes, tends to be deeper and more illuminating than anyone expected. Newton's anomalies led to the geometry of space-time. Classical radiation anomalies led to quantum mechanics. Each resolution did not diminish what came before. It revealed it as a special case within something grander. If Lambda CDM is indeed incomplete, then the resolution of its tensions will not diminish its achievements. It will reveal them as the foundation of something deeper, a model of the universe that includes whatever dark energy truly is, whatever additional properties dark matter possesses, whatever modifications to gravity the largest scales require. The 6 parameters will not be discarded. They will be understood as the first 6 terms in a longer equation. And the James Webb Space Telescope, the $10 billion instrument that was built to refine the picture, will be remembered not for confirming what we already knew, but for showing us, with a clarity that could no longer be denied, where what we knew stopped being enough. The universe does not owe us simplicity. It does not arrange itself for our convenience or structure its laws to fit neatly into the frameworks we construct. For 2 decades, it appeared to cooperate. Lambda CDM worked. The predictions matched. The measurements aligned. The cosmos seemed to be playing by the rules we had written down. Now the instruments have become sharp enough to see that the cooperation was not quite perfect. The edges are showing. The residuals are growing. The universe is gently, patiently, insistently telling us that our best description of it is not its final description. That is not a failure of science. It is the entire point of science. To build the best possible model, to test it with the best possible instruments, and to follow the evidence wherever it leads, even when it leads away from the framework you spent decades constructing. Cosmology is entering a period of deep uncertainty and extraordinary opportunity. The most successful model in the history of physical science is bending under the weight of its own precision. The instruments that were built to confirm it are instead revealing its limits. And somewhere in the gap between what the model predicts and what the universe shows, there is a deeper truth waiting to be found. We do not yet know what that truth looks like. We do not know whether it will be a small correction, a new parameter added to the existing 6, or a fundamental reconception of how the cosmos works. The data that will answer that question is being collected right now by telescopes on mountaintops and satellites in space, by spectrographs splitting the light of millions of galaxies and detectors recording the faintest whisper of the ancient microwave sky. What we know is this: the universe is not quite what we thought it was. And the instrument that revealed that, with its golden mirror and its infrared eyes floating in the dark 1.5 million kilometers from Earth, is still watching, still measuring, still collecting the evidence that will eventually show us where our understanding ends and where the next chapter of cosmology begins. The model is bending, the data is clear, and the universe, as it always has, is waiting for us to catch up.